This is a note video on section 1.2 precalculus entitled Functions and Their Properties. Keep in mind when you're watching this video, what you're going to want to do is watch part of the video, pause it, make sure you have proper notes, make sure you get all the information written down, and then press play. You might have to play, rewind, pause, play, rewind, that sort of thing when you're watching this. I'm going to try to go fairly quickly so as to not have the video be too long, but with doing that, you do need to be able to play and stop and write things down as you're watching. So the objective today is that students will be able to represent functions numerically, algebraically, and graphically, determine the domain, range for the functions, and analyze the function characteristics such as extreme values, symmetry, asymptotes, and end behavior. We'll start with domain and range. The main things that you need to realize about domain and range are the domain is all of the x values that you can use in your function, and the range are all the y values that you can use or have. So basically, when I ask you to find domain, I'm asking you what are all the x values that your graph hits, and when I ask you for the range, what are all the y values that your graph hits. Domain is also considered the input, and the range is considered the output. Whenever you describe the domain and range to me, you're going to use interval notation. So unless it's all real numbers. If you can plug in any number for x, just tell me all real numbers. If you can plug if you get any answer back or all answers are possible for y, then the range would be all real numbers. If we had the graph of the basic parabola y equals x squared, well, you know that graph looks like this, where the vertex is at the origin. So in this case, our domain would be all real numbers, and we would write domain all real numbers. The y values that are hit, though, are only from 0 to infinity. There's no negative values that are hit. So what we would do for the range is we would write range to be from 0 to infinity. And the range is the only question I'll ask where you use interval notation and actually use the y values within that interval notation. All the other times you're going to use the x values when describing a range of numbers. As far as function notation goes, understand that we're going to use Euler's function notation. Y equals f of x, which is what I just read. Y equals f of x, or we could say the value of f at x. Here we call x is the independent variable, the input, or the independent variable, or the x value. They're all the same thing. And then the output, or the y, is considered the dependent variable. You will have to be able to determine whether something is a function or not. Just keep in mind, it's a function if every x value or every input gives you exactly one output. Okay? You can have different inputs that give you the same output, but you can't have one input or x value give you two different outputs or y values. If that were the case, then it would not be a function. You can see that in this mapping. Over here, the domain is the x values we have. You can see how this x sub 1 goes to y sub 1, and x sub 2 to y sub 2, and everything just goes to one value. Every x will give you one y value back out. It's okay that the x sub 3 and the x sub 4 both went to the same y value, That's fine. What's not okay is if you look over on the second little mapping over here, it's not okay that this first x sub 1 can be mapped onto y sub 1 and y sub 3. If that happens, it's not a function. A nice quick way to check and see if your function is a function graphically is to use the vertical line test. You can just take your pencil or whatever vertical line you have and slide it across your graph. As you slide it across your graph, that line intersects the graph in more than one spot, then it's not a function. As you can see, I slide this line across the graph shown, it always only hits at one spot. Same thing here. It's always hitting at one spot. Same thing here. Oh wait, no, stop! Oh, right there. We hit the graph in 2 spots and even 3 spots all throughout here. That means graph C is not a function. Get it? We call that the vertical line test. Make sure you're making note of all this stuff. So here's an example where we'll find the domain. If you simply look at this function, what you're going to look for when finding the domain, you're finding what x values can I use. So what you're going to want to look at is, are there any restrictions on my x values? Well, what are the main restrictions we come across? Well, we can't have a negative in the square root when we're graphing. We can't have a 0 in the denominator. Those are the 2 biggest ones. So you can only use x values that allow you to have a positive number or 0 under the square root in this case. So what's my restriction on my domain? Well, if I use any x values less than negative 2, I'd have a negative number. That means my domain must be all values from negative 2 and greater. That's how I would list my domain. You could see that in the graph or just solve it algebraically. The range is sometimes harder to figure out without a graph. It will be easier once you are more familiar with the 12 basic functions, which we'll talk about very soon. But in this case, we'll just graph this one to find the range. So if we graph it, we have something that looks like this. Remember, range, what I'm asking for range is what y values can I hit or can I use or will I get as an output if I include all the different inputs that I can. So if you look at this graph and if you put it in your grapher, you can play around with the window and see if you ever hit the numbers that you're wondering about. But basically what you're finding, or what you should find, is that the graph is going to go up infinitely far on this part of the graph, and as you come this way, you're going to get infinitely close to a y value of 0, but you're never going to quite hit it. The same thing's going to happen here. If you go to the left, you're going to get infinitely close to a y value of 0, and as we go this way, well, you're going to go down forever towards negative infinity. What does that mean? That your range is going to be all real numbers except 0. All real numbers except 0. So you could write that, your range, as going from negative infinity to 0, but not including 0, or from 0 to infinity. Or you could write it out in words. The next element of a graph or portion of it, analyzing a graph that I'll talk about is continuity. That's basically asking, is the graph continuous or does it have some sort of discontinuity? Sometimes I may ask, is it continuous or non-continuous? So basically it's continuous. If you look at the top left graph here, it's continuous if you can put your pencil down on the paper, follow the graph, and basically draw the whole graph without having to pick up your pencil. That's considered continuous. If it's not continuous, well, then you have to pick up your pencil to complete the graph and put it back down. There's 3 different types of discontinuity that I want you to know about: removable, jump, and infinite. There's 2 types of removable. In the upper right here, there's the removable where there's basically a dot missing. You got to pick up your pencil, and it's placed somewhere else. It's placed up above, and then you basically continue the graph almost like you didn't have to pick up your pencil. That's one form of removable discontinuity. The other form of removable discontinuity is where there's just a point missing. It's removed, if you will, and then you basically put the pencil down right next to where you picked it up from. That's also considered removable. So sometimes that point is removed and placed somewhere below or above where it should have been. Sometimes it's just removed. Jump discontinuity, the bottom middle graph here, shows how you follow your graph along and all of a sudden it jumps vertically, either up or down, and then continues up. That's called jump discontinuity. And then the last one is infinite discontinuity, and that's where your graph is heading infinitely in one direction. You got to pick up your pencil and head in the opposite infinite direction. Continue. Start from infinitely high and come back down. Basically, you're going to have some sort of vertical asymptote there, which we'll talk about later. The next portion of analyzing a graph that I want to mention is being able to describe increasing and decreasing or constant portions of a graph, or increasing, decreasing constant functions, and also what interval they are increasing, decreasing, or constant at. The upper left graph here, real simple, it's increasing. Basically, you're always going from left to right. You are always going from left to right. And if as you go from left to right, you are constantly getting higher or going up farther, or the y value as you go to the right increases, the graph is increasing. In the upper right, it's always as you go from left to right. If you go from left to right, if you're decreasing in the y values, your graph is decreasing. So in the upper left graph here, I would say it's increasing for all real numbers, and that's talking about the x values. For the upper right, I'd say it's decreasing for all x values. Now on the lower left, this is constant. That's where the y value stays the same. And then on the lower right, we've got different things going on here. So the way I would describe this one is the graph is decreasing on the interval from negative infinity to negative 2. It's going down. It's constant from negative 2 to 2, and then it's increasing from 2 to infinity. And just make sure that you include all points that are included on the graph. Any one particular point is not increasing, decreasing, or constant. So it's okay that they use brackets both here and here, including it in both spots, because any one point isn't increasing, decreasing, or constant. It takes a range of values. And that's basically what this section talks about. So you can pause and read that if you need anything more about that. So here's an example of a graph that I'd want you to analyze the function for increasing and decreasing behavior. Basically, you could graph this. What you can do is you just take it piece by piece. You shouldn't have to graph it, but you can. Maybe at this point you would need to. Have a graph. There we go. Basically, what's going on is this portion of the graph right here is telling us what the graph looks like for the different x values over here. What I mean by that is this is saying this right here is saying you're basically going to have the graph y equals negative 5 when x is less than or equal to negative 3. Well, that's being shown down here on the graph, this part right here. So what that means is, that tells me the graph is constant from negative infinity to negative 5. It's constant. Then the next part tells me y equals 2x plus 1 is the graph I will have for the x values from negative 3 to 2. Well, the graph y equals 2x plus 1 I know is the graph of a line with a positive slope of 2. So that's this part right here. So that's increasing. So we would write increasing from negative 3 to 2. Again, you could use parentheses or brackets. I kind of look at what's shown up here in the range to determine mine, but I'm not going to be real picky on that. And then finally, the last part shows y equals 5 if x is greater than or equal to 2. That's this part of your graph, purple. So I would say constant again from 2 to infinity. And that would answer that kind of question. That's all the notes you need for the first assignment. I'm going to keep going with notes till I have one video for the whole section, but basically the first 15 minutes will cover the first assignment.